Okay, so hi all, and welcome to this first video in our last unit, which is on Laplace transforms, which sounds like a very fancy thing. So jot that down. Transform, sorry, that should be one word. I don't know why that's up two. Which I'll get into in a second. Just a couple housekeeping things first. So hopefully you had a chance to look at your exam number 2, which is posted. If you click on exam 2 in Canvas, you can see that I uploaded the corrected version of your exam, so you can take a look through and see how you did. Overall, I think we did pretty well. I didn't actually write down or compute an average, but anecdotally, I don't know, it's got to be in the B's somewhere. Anyway, so it seemed to go pretty good for most people. So good, and I think we have worked out the kinks of our take an exam at home and scan and send system. So, which thankfully we will only, I think, be using one more time, maybe 2. We'll see, but. As we head into this last unit. So in these whatever 3.5-ish 4 weeks that we have left, we will do this one last unit, Laplace transforms, and do an exam on this at the very end of the semester. So I think you maybe heard, or if you haven't officially, I'll say that the final exam week has been, I don't want to say canceled, but transformed into just a regular week. So the week where we would have done a final exam, or where you would have taken final exams in all your courses, is now just a regular week of classes or whatever it is that you're normally doing for your courses. So, which may include, and probably a lot of, since most of you are in STEM, I have a feeling that most of us in STEM are still giving some sort of an exam during that week, whether it's a final exam or just a regular exam. So obviously, be in touch with your professors about that, or they will be in touch with you, I should say. But for us, we're going to do just an exam number 3. So we've of course done 2 regular semester exams, and we're going to do one more on just this stuff, and that's. And so we will not do a final exam as we probably would have normally done. Mostly because of the fact that we missed a whole week, and obviously other kind of logistical things. So we will have one more exam score that goes into that pot. If it's looking like we'll have time, we'll do a quiz. I think maybe we don't all always say that we like the quizzes, but I will assert that we do all like the quizzes, in the sense that it kind of gives you 2 shots. You can kind of mess some stuff up on the quiz, and then get the opportunity to kind of revise and fix by the time the exam comes around. But we'll see. So if it seems like we're going to have time, we'll squeeze in a quiz. If not, then we'll just do this exam, and that'll be it. So, but at least the main point in bringing this all up is just to say we won't be doing any cumulative things. And so, as much as you're welcome to ask questions if you do have about from your exam number 2, we're not going to be doing that material anymore. I should say we will kind of revisit spring problems, though, the vibrational problems, once we have this new found skill of doing these Laplace transforms, since they will be coming back to us. So, okay, anyway, sorry, that was the course update. Usual things this week and next week and the week after, which are, of course, lecture videos for you to watch. There'll be probably 2 more WebAssign homeworks. And like I said, if we have time, we'll do a quiz. Maybe we'll even just do a fake quiz. By that I mean, hey, here's a quiz. Do it and check yourself kind of thing, rather than an elaborate, let's get this all fancy. So, okay, anyway, enough about that. On to the material. So Laplace transform. So before we launch into what this is, and it's going to be a little bit strange of a thing to do at this point, it's not going to seemingly be connected to ODEs, but it will be at some point. So before we get to even the preliminary of the preliminaries, just a quick calculus observation here. So of course recall, since we've done you've probably done this integral, a million times, well, not a million, dozens of times just in this course, and probably hundreds of times total, that we certainly know that this is one of our favorite integrals to do. All right, or antiderivatives to do, and E is always our friend because, of course, it's so easy to do integrals and derivatives. This, of course, is there is a simple U substitution here, since the exponent is CT rather than just T. But of course, hopefully we have this one almost on autopilot at this point. That would just give us 1 over C. It's big. 1 over C, e to the CT. Right, so it's essentially the same thing, just with this. The exponent sort of contributing, I guess I would say, a term in the front there, the 1 over C. Now, somebody smart decided or observed and thought, so E is kind of, it seems like E is the answer to everything, right? Most of our solutions that we've, even in the first part of the course, often had E's in them. And again, thinking back to what E represents, it is the natural growth constant, so maybe in some sense it makes sense that that appears in many places. But E has some other wonderful properties, of course, that even just looking at this integral, it on the one hand, integrating E gives you kind of the same thing. And I say kind of because, of course, it does. You still get E to the CT, but you do get this contribution, which is simply related to the exponent, right? Or in fact, more so specifically, the coefficient of the exponent if it just has the T there. So somebody looked at this and thought, well, so if we could exploit the properties of E, what does this seem to be saying is that even through integration, or I should say with integration, E kind of mostly is stable, you might say. E turns into E. However, if you just got E, E to the T goes to E to the T, well, okay, that's pretty limited in what you can do. What is this saying is that this exponent here, this C here, is, I would say, transformed, if you want to use the word that we're heading towards, as a coefficient. And of course, we know about, from algebra, or I guess pre-calc, that of course we treat exponents, when we have issues up in an exponent with E, we ln it in order to get the exponent down, even if we don't have an E there. So we know that we would much prefer to work with issues, I guess, if they were, so to speak, on the ground, rather than up in the exponent. So that's my 3-minute motivational speech for why what I'm about to write down is actually a really clever idea, which is to do what's known as a transform, and we'll look at the Laplace transform of a function in order to help maybe recast it in a different light that might make our lives a little bit easier. Okay, so that's the intro speech here. So we know this, and let me also recall one more thing. I'm going to call that recall 1. And also recall number 2, that if we had bounds, I know it's been a while maybe since some of us have thrown some bounds on an integral to make it a definite integral, that you know this one too, of course, just a reminder, right? When you have bounds on an integral, it means, of course, you plug in the top number. When you finish, you plug in the top number, and you subtract what you get when you plug in the bottom number, right? So, of course, if I have 0 to infinity, which is what we're going to be doing many, many times here, then I do the antiderivative, fine, we know that. But then remember, of course, we do this little thing where we plug in the two bounds, in this case 0 to infinity, and we see what we get. Well, what do we get? So let's see. Here I'd end up with, right, and of course, as I'm writing this down, just of course, we're viewing C as a constant, right, a number. Where and t is our variable, right? We're doing dt, right? So t is the variable here for the integral. So I get 1 over c, and then when I plug in infinity, which you can't really do, but I'll just sort of I'll cheat and say it anyway. C times infinity, and then remember you get minus, what do you get when you plug in 0? 1 over c, e to the, sorry, I don't know why that looks like c to the t, it's just c times t, to the c times 0. Okay, so just like you've done before, this is how we evaluate a definite integral, is that we plug the bounds in at the end, and then we see what we get. Well, let's see, what do I get? I'm going to put a pin in the first one for a minute here. Maybe I'll keep going this way. So let's see. So certainly c times infinity is big. Now, of course, the question is going to be, is this positive or negative infinity? And that's going to make a big difference. So let's leave that alone for a minute. But the second one's a gimme here. E to the 0 is 1. So, of course, that's 1. And then I just have 1 over c. So how much is this? So let's take the pin out now. Now, if c turns out to be positive right here, then, of course, infinity times a positive number is just infinity. And e to the infinity is super infinity, and dividing by c, who cares? So this is going to be very big if c is positive. On the other hand, if c is negative, right? If c, oh, and I should say, if c is 0, we're already dead, because I can't divide by 0, right? So if c is positive, I'm in trouble. This is infinity. If c is 0, while that would be 1, this would be 1 over 0, which is infinity, right? Okay, so I got infinity. I got an infinity minus infinity, but let's not deal with that. Okay, but for sure, if c is negative, then of course this is a big number, but negative. And we all remember that a negative big number in an exponent means the whole thing goes to 0. And then dividing by c makes it even more so go to 0. So this will go to 0 if c is negative, which means I would just be left with this piece, which just stays put, right? There's no limit here. So I think if we wrap that all into a nice little package here, we could say, so how much is this? Well, it blows up if c is greater than or equal to 0. So, let me do it this way. I'll copy this down one more time. But it's negative 1 over c if c is negative. And so, of course, it would make this whole expression positive if that was the case. C being negative 1 over c would be positive. Aha. So this is just a fun calculus reminder of some things. But I think, right, that if we're not looking for infinity, which, I mean, usually infinity is a game over moment in terms of trying to do any real math, as long as c is negative, if for whatever reason I'm doing this computation, I'd end up with not infinity, but I would just have a nice positive answer. Okay, so that's all just food for thought, I guess, and things that you already know. So let's define the main character of our story for the rest of the course here, which is this Laplace transform business. So we define the Laplace, which obviously that's a person, a mathematician, Laplace transform of some function, little f. Oh boy. Okay. To be the following. So jot this down, and we'll pick this apart a little bit here. So we'll switch to, I'll give you two notations here. I'll give them to you both right now. So one not surprising way that we might write the Laplace transform of a function is to write a script L, and then if I have little f to start with, then I maybe say the Laplace transform of f. That's just sort of like an act, like a verb, I'm doing an action to this, I'm transforming it. So that's one notation that you might see. We'll more commonly use, so these first two things are just notation. We might more commonly do the old, let me go to a capital letter. Now I know we use that in Calc 2 and I guess Calc 3 maybe even, to say that's the antiderivative. So I don't want to confuse you, right? It's not the antiderivative that we're talking about anymore. And to help us better see that, the Laplace transform uses s as its variable as opposed to t. I think it's an awful choice that we used s, because of course historically in math, s's are a disaster because they look like 5s a little bit. So, but since this is the standard notation, I won't disagree with hundreds of years of people smarter than me, and we'll stick with the s here. Right? So these both mean take the Laplace transform of this whatever function you start with. Okay, so these are both just notations. I think we're mostly going to be using the second one here. Okay, now finally, who is this actually? So those are just notation. But who is this? So it's going to ask us to do an integral, and an integral that has bounds. We're going to go 0 to infinity. And we're going to do e to the negative st f of t, and then we're going to integrate over t. So jot that down. That certainly gets a star or something. That's the definition of this character. But before we launch into let's try this on a few examples, which we will, just at least to say a few words about this. So note several things here, I guess, right? One, the transform, right, whichever format we write it in, is a function of s. I'll put in parentheses here, not t. Okay? All right, and how do we, know that, or how should we think about that happening? Well, what's going to happen when I do this integral? Well, of course, looking at the integral here, I have s's and t's. I have a mixture of s's and t's. Now, in some sense, that can be a little bit confusing when you have more than one variable. But I'm going to unconfuse you immediately by saying, but t is the variable as far as the integral is concerned. We know that that's what the dt sitting over there means, among other things, is that it tells you who's the variable. T is the variable. S is the variable for f, for big F, but within the bounds of the, in terms of this integral, though, the only variable with the integral is t. So if you're going to do this integral, and we'll do a few of these in a minute, we're going to treat s like a constant and t as the variable, right? So now my result, of course, is going to have s's in it, because of course I can't just ignore it. But, right, so it's a little funny when the first time you ever see a transformation, and I should say transforms are a big part of any sort of higher math, especially in engineering, where they are essential for quite literally transforming hard, impossible problems or very hard problems into slightly easier ones, which we'll see that happening with our ODEs in a future video. But the idea here, right, is that s, right, so I'm building or I'm defining or I'm creating a function of s, and I'm telling you, oh, okay, how would I define big F of 2? Well, I'd put a 2 in for s, and then I would do this integral. But the integral says, t is the variable for the integral, so I do a regular old, t integration thing and plug in my bounds. But of course, whatever I plugged in for s, whether it's just a generic s like it is here, or whether it would be a number, that would probably be still part of my answer. All right, so that's why I say down here, big F, or the transform of little f, is a function of s, not t. Right? In particular, in doing this integral, you will treat s as a constant. And t as the variable, because it is, that's what the dt means. All right, and of course, as a result of doing this integral, you're going to find the so once you find the antiderivative, of course, you'll plug in infinity and 0 for t. So remind yourself for t. And after you simplify, that meaning only s's, that looks funny, but you know what I mean, s's, only s's will survive. And numbers, obviously. Okay? So in other words, you're not going to have any t's in your answer to this integral here, because you're integrating over t, and then you're plugging in 0 and infinity for t, which means all the t's will have vanished, and you probably will just have a bunch of s's running around, again, with some numbers or some other things. Okay, so Now I'm going to, again, give you a 60-second thought on what is this? What does this do? Now we're going to see this in action, and maybe that'll make a little more sense when we do. But essentially, this name is very good, transform. If I say I transformed something, hopefully that means to you something more than just, oh, you made it different. I mean, yes, but I think if you really try to drill down on what is a little more scientific way of saying you transformed something, might mean you started with something, and you transformed it into an equivalent something. Maybe not always, right? I'm thinking of, a Rubik's Cube or something like this, where you've got to try to solve this puzzle and you keep changing it into something else. Okay, maybe in that case, the changes you make are making it different. But a transform in math and elsewhere really doesn't mean, let me just change this into something totally new. It really means take something and transform it into an equivalent version of itself. That's what this is going to do. Now, the reason why that's going to be important is because later on, you're going to want to go backwards and go back to and sort of reverse transform to get back to where you started. The best human example I can think of for a transform is something like a language translation. So if I have a sentence in English and I translate it into Spanish, and then maybe I edit it a little bit, I put some extra words in or add some other thoughts. If I then translate it back to English, it hopefully, two things. One, the essence of what you started with was still represented. And if you did make some changes and to make it better somehow in Spanish, those changes are reflected when you go back to English. And that's actually what this is going to do for us, is we're going to, believe it or not, be able to use this to help us solve ODEs, where we're going to take an ODE, we're going to transform it via this. That looks scary for now, but it isn't. Solve it. And then we're going to get a transformed solution, which we're going to back up to get back to the solution, the regular solution. So that's where we're headed with this. This takes a little bit of time to get off the ground, but that's going to be the idea. All right, so before we get into that, though, how about just some easy examples of doing transforms of famous functions, I suppose, and some general properties of transforms here. All right. So let's try this. I mean, I know no function easier than just a constant. So how about we take, I'll say k, where k is a constant. I won't use c just to not confuse us with our intro problem here. Although, to be honest, it'd probably be okay. But anyway, so let's just take a function that happens to just be a horizontal line, right? Y equals a number. Fine. So what happens when we transform this? So let's do that. So the Laplace transform of, now you'll see this node, either if I gave you a function, I could say the Laplace transform of little f, because that's this function, or you might even just see the function itself, right? If it's cosine of t or something like that, you could just put that into parentheses, right? In order to say transform that, right? Of course, we're using, I don't mean to be killing you here with notation, but we're going to use this big F of S to be our transform. So big F of S should be what? All right, so by definition, I would say do the integral from 0 to infinity of e to the negative st times f of t. I'll just write it out once again. So that's just the definition. But now if I fill in my function is just a number, k. All right. So, all right. So let's see. So, of course, k is just a number, so it's an integral. So we know we can just pull numbers out in front if you want. And now I'm just left with this. And we did this problem a minute ago, right, at the start of this video. This turns into, right, so e to the negative st. Let me just remind you that we did this problem. I used the letter c instead, right? But what did we get? Oh, sorry, let me point to this one. When we did e to the c, we got negative 1 over c. So e to the negative st, which is what we're currently looking at, e to the negative st, I'd have negative s down here, and the two negatives would cancel to make 1 over s. Okay, I'll say C intro problem, right, where C is really negative S. Okay, or just do the integral, right? It's not like it takes that long to do. Okay, but now what did we say at the beginning? We said that this only worked, so I should have pointed to the bottom here, right? This only works if this is negative. Okay, so I'll say that again. If this is negative, then you get this. Oh, so what's here has to be negative. Oh, what does that mean for this problem? Oh, that means what's here has to be negative. Oh, well, if negative S has to be negative, I think that probably means that S has to be positive. All right, so I'll just write this down as a fraction. And this works as long as S is positive. Okay, so let me read this to you from top to bottom. So if you had just a constant, 5, for example, and you wanted to say, what's the transform of 5, of the number 5? It would be 5 over S, where this is only valid, right? So this is sort of the domain, if you want to go back to pre-calc, right? So this is the domain of big F, of this function we're defining here, right? We're making a function called big F of S, which happens to be called the Laplace transform. And, okay, I'm going to define for you, I'm going to say, so if you had a function that was just a constant, then the transform of a constant is actually just a constant over S, where you're only allowed to do this for positive S's. And again, that's so that the integral doesn't blow up. Okay, so we've successfully computed our first Laplace transform, so that's kind of exciting, I guess. All right, so in particular, of course, 1, if you were doing the Laplace transform of just the number 1, you would just get 1 over S. Okay, let's just try another one just so we can see a little more of what might happen. So let's actually try a little more complicated function. Maybe we'll do an E function, and to make it a little more interesting, I'll say maybe e to the, rather than just e to the t, maybe let's throw a number in there, so e to the at, where obviously a is a constant. So e to the 5t or something like that. Okay, so let's see, what do I get? So I'm going to take the Laplace transform, which is going to say, okay, do this integral, and negative st, that always goes first, and then whatever your f is goes second, and then dt. Okay, so that's just the definition once again of the transform. Okay, now, all right, well, let's see. So just keep telling yourself, s is a in terms of the integral, s is a constant, t is the variable. So of course a is a constant as well. So these are both constants, s, negative s, and a are both constants. So I might say to myself, well, I could at least group those together. And I can't pull this s out in front like we did in the last, or in one of the examples, because it's not, s is a constant, but st is not. So let me just do a little reorganizing here at least, and let me at least put these together. So you could write this either way. You could do a minus s, or s, negative s minus a, or something like that, whatever you want to, whatever makes the most sense to you. I'll go with a minus s t. Right, so this is just algebra, so just putting those together as a common exponent, which of course means you add the exponents, and then of course since they both have a t in them, I'm going to factor out the t. And so I'm left with this, which once again looks an awful lot like our little intro problem, where I said if you have e to the any number times t, you simply get negative 1 over that number, provided that that number is negative. Okay, so I got to unpack that for what we just did. Again, you could just do the integral, and you won't have to keep flashing back in slides, but I'm going to be lazy here and say because of our intro problem, this turns into 1 over negative the exponent where the exponent has to be negative. That's, I think if I read that correctly, right? That's just exactly this guy, right? So you have a c here, So you get negative 1 over whatever was there, and the whatever was there has to be negative. I think I unpacked that correctly, hopefully. I put the negative on the bottom rather than on the top, because I'm probably going to distribute it right now, but same idea, of course. So, of course, writing this like a normal human, I would probably say, oh, okay, so what do I get here? That looks like s minus a to me. And maybe rather than where, I'll say for. Now, what has to be true about s? So in this case, s has to be greater than a. Okay? So again, this is the domain. Of this particular transform. Okay, so let me read this to you from top to bottom. So for the function e to the at, which is a very common character that we've seen in a lot of problems all year, e to the at, okay, you want to do the transform of that? All right. Well, as it turns out, it's just this, where this is only defined, or this only works, the transform is only valid when s is bigger than whatever this number is, a. So if a happens to be 5, then e to the 5t, you can do the transform, but you can only plug in s's that are bigger than 5. We'll see when we use this that that's not going to be a problem, but okay. So before we move on, what I'm going to try to show you here, now in the first one, I might actually say that let's compare the complexity of our starting point and our ending point. So our starting point said we were going to do the Laplace transform of just a number. Oh goodness. And when I transformed just a regular old number, I got not a number, I got a function. I got s's. Okay, so that seems like maybe a bummer. So in other words, if I'm trying to say which of these is simpler, the thing I started with or the thing I ended with, I would definitely say the thing I started with was simpler. So this idea of doing a Laplace transform, okay, on a constant seemingly makes it worse. Okay. But let's check in on this one. So now our final answer here was for e to the at. Right, that was what we started with up here. So our bottom line here, sorry, I left the boxes around these as I was doing. So I think let's look at this one. So I started with e to the at. Now, while e is our friend from calculus and all of that, e to the at is a fairly complicated function. It's an exponential. You can't even solve for t without doing an ln. I mean, this was our enemy, to be honest, in pre-calc and algebra, because it's messy. But look what it actually turns into when I do the transform. I just get a nice, reasonably simple fraction here. I have no e. I mean, the e is completely gone. I don't have ln's. I don't even have anything too complicated here. Remember, s is a variable and a is a number. So let's say I did the transform of e to the 2t. I would just have 1 over s minus 2. That's a very simple graph. It's actually just it's the inverse of a line. No big deal. So in this case, I might call this more of a win, that a more complicated function was transformed into an easier one. Maybe that remains to be seen whether that's going to actually be good or how that's useful. Maybe that remains to be seen. But who else? So I'm just going to state a couple of others here. And of course, there's a chart that you're going to see on Canvas posted that sort of is, kind of like the derivative chart. It's just here's all the famous functions and their transforms. Rather than us doing this by hand every time, which I'm already sick of doing this by hand, we're just going to be able to appeal to the chart and say, oh, okay, well, tell me, I want to know the transform of cosine or something like that. Well, let me just look it up, right? So I will say, before I start writing a couple of other characters in here, I probably will, though, I will have you do some by hand or some the long way, as we just did these first two, on an exam or in some sort of assessment, in order to just sort of not have this be 100% like, oh, I just looked this up in the chart. Oh, I just looked this up in the chart. So, kind of similar to calculus, where we tortured you a little bit and made you do a couple derivatives the long way before using the shortcuts. Same thing here. So don't totally just be like, cool, so I don't have to remember anything from that first half hour of this video. Yes, you do. Okay, so just make sure you're competent and able to do these by hand if you really needed to. But I'm going to stop and just give you a few other famous guys that we might need. So we got a constant. Oop, that was our first one. So the transform of a constant is just that constant over s. The transform of E is 1 over s minus whatever the x coefficient of t is. Who else? Probably we want to know about trig. So if we do, I'm not going to do this in the shorthand here. So if I wanted to know about the transform of cosine or sine, those are famous guys that we often see in our problems. Then these, you have to do a little more work, and you have to do a little bit of integration by parts to get to these. But if you do, it turns into a wraparound integration by parts. You end up with sine turns into s squared plus a squared, and cosine turns into s over s squared plus a squared. And these are both work for positive s's. Okay, so that's trig. So we got E, right, and again, right, these come from doing this integral and doing some work. Now, I got to be honest, right, those are, like I said, these require a wraparound integration by parts. So those are the ones where you do it once and you get something that doesn't look great, but then if you do it again, you get back to the one you started with, and then you can solve, right? So that's how you get both of these. But again, just like we saw in the last with E, cosine and sine, I mean, those are super complex, complicated functions. And yet, in Laplace world, they turn into just, I mean, sure, this is a number over a parabola. That's what s squared plus a squared would be. Remember, a is a number. So this is, 2 over s squared plus 4, or something like that, maybe. Okay, I mean, that's got some complexity, but it's still just it's an inverse of a polynomial, or reciprocal of a polynomial. Way easier than trig. I mean, think about how hard it was to get trig off the ground when we first learned trig. So I'm going to say, at least in the examples we looked at, it looks like, looks like that the Laplace transform might take more complicated functions and turn them into essentially just polynomials, algebra functions. I eliminated trig and got rid of it and said, hey, you could just work with algebra. We eliminated E in the last example. We had E to start with, and we squashed it and ended up with just, again, a reciprocal of a polynomial. And in fact, when we look at all of these characters, we're going to essentially, or not essentially, we will end up with just polynomials when we do the Laplace transform of just about anything. Most things anyway. So the idea, and this is a little hard to see, and maybe if you're really, really thinking hard about this, you might, but the idea of what a transform does in general is that, again, it takes a harder problem or a harder, more complicated thing, and it tries to transform it into something easier. So what does this do then, or how are we using this for an ODE? Well, let's try that. So I'm just going to leave, let me just list one more that probably we might want to know. How about t to some power? Oh boy, this is one that, am I going to mess this up? I don't have the chart right in front of me, but oh gosh. It's right, okay. You get n over s to the n plus 1. Ooh, is that a factorial? That might be a factorial. Okay, maybe don't hold me to this one. We'll look that one up on the chart. So that's probably also for positive n. Okay, but this would put an asterisk next to that. Double check when we look at the chart here. But this is, these are our building block characters, right? Constants, no big deal. E, no big deal. Oops. And trig and polynomials, no big deal. So how are we using this then to do ODEs? So I'll do this last computation here. And and we'll see what we end up with for doing the transform on ODEs. Well, let's see. So so how does this apply to solving, or at least just to ODEs in general? So what does our ODE usually have in them? It has things like y and y prime and y double prime, if it's a second order ODE, which most of these will be. So, well, of course, right, just notationally, if y of t, right, or just y, is our is the main function in the ODE, that we're trying to solve, then we're not going to be able to say much about this. So I'll just remind us, then we'll use Laplace of y to represent or to mean its transform. Okay, that's just notation, right? Again, or I won't use the big F here. And more so, we're going to use that on each part of the transform. So if we have an ODE in front of us, of course, the characters in my ODE are things like y and y prime and y double prime. So for the y that might be in our ODE, if we try to transform it, we're just going to write that as Laplace of y. Now that's sort of just a notation, right? We haven't actually done anything, but that's fine. You'll see why when we get to our strategy. But how about the other two? How about y prime? Well, I'm going to claim that actually the Laplace of y prime, or y prime of t if you'd like, is actually something we can compute. And by compute I mean simplify or resolve. So let's do this. So, all right, well, by definition I should do this, and then I should do that, and then I should do y prime, and then I should do dt. Okay, so I would say, all right, I want to do this integral. Great. Well, I was able to do the three examples that we did earlier, mostly by saying, well, I can actually do the integral and plug the bounds in and get an answer. Well, in this case, obviously I don't actually know what y prime is. That's the whole idea, of course, is that I don't know who y is. It's an ODE. So if I don't actually know y prime, I don't think I'm going to really be able to actually integrate this thing. But what can I do? Is I can say, well, if I was going to try to do this, I might try integration by parts. And the reason why I would try that is because, well, I can't actually do this. But integration by parts might work, and in particular, if you remember, integration by parts asks us to think about one thing times another thing. And remember in order to do this, I just have to say who's playing the role of u, I think it's our usual notation, and who's playing the role of dv, or v prime. One of these is u, and the other one's dv. Well, think about this for a minute, right? If I'm trying to figure out who's who in all of this stuff here, whatever you choose for u, you need to be able to do the derivative of. Well, so if I choose this for u, when I do the derivative, I'm going to get y double prime. That probably doesn't seem like a great idea, because that seemingly is making my life more complicated to go now to a second derivative. So how about I pick y prime to be dv, which means what's left would be u. Okay, well, du is the derivative of this, so that's no big deal. That's negative s e to the negative st. That's just a chain rule. And then if dv is y prime, then v would just be y, right? dv, right, that's the derivative of v. If that's y prime, which obviously is the derivative of y, then v and y are just the same thing. No. Okay, so if I tried one round of integration by parts, sorry, I don't know why it keeps doing that, I get u times v, so that's, of course, e to the negative st times y. I'll put this as y of t. It's this guy, right? Y of t, u times v. Now, that's out of the integral. So, of course, back in Calc 2, we had to remind ourselves, since this is a definite integral, we have to remind ourselves we do have to plug those bounds in. So we'll say that. But then I still have an integral left, minus the integral, same bounds, of v du, right? These two guys, v du. Okay, so let's see, what do I have here? V is y, which I'll write as y of t again. Du is that stuff. And I'm doing integration with respect to t. Okay, well, this looks not great, but all right, let me carry on here. So how about the front piece here? So remember, I'm plugging things in for t here. So if I plug in t, we're going to again take s to be positive. I'll write that down at the end here. So, but we're going to take, or I'll remind ourselves, we're going to consider positive s's only. So if s is positive, and I plug in infinity for t, this is a positive number, a big number, but then with this negative in front, this whole thing is negative big number. Negative big number, and an exponent, of course, drags you down to 0. So when I plug in infinity, I think we should end up with 0. And then minus, what do I get when I plug in 0? Well, that would make that 0. So, of course, that's 1. And then I would just have y of 0. Okay, so that piece is done. Now this thing over here, let me organize my thoughts here. I have a minus and another minus, so that feels like plus. S is a constant when it comes to this integral, so I can pull this s in front. And then what am I left with? I'm just going to rearrange here. I'm just left with that. Now that should look awfully familiar from about 30 minutes ago. This is just the definition of the Laplace transform of y. So what do I end up with? I end up with, I'll put this guy in the front just because it's positive, so I'm going to have s. This whole integral, right, this is just the Laplace of y. Okay, that's just our original definition. So I get s times Laplace of y minus y of 0. Oh. Well, y of 0, that's not an unfamiliar character, especially when I'm talking about ODEs. Isn't it true that usually when we have an ODE, we're given, especially if we're going to find the constants at the end, we're given y of 0 in order to know what to plug in to try to find C1 or C1 and C2? So this is a number that I'm probably given. And what is the good thing about what just happened here is that I said, well, if you're trying to transform y prime, you actually just get the Laplace of y with some other stuff. As I guess maybe loosely how I would say this. Okay? So, let me repeat this at the bottom here. So that's a good one to know, since we're heading towards using this for ODEs. And similarly, I'll just jot down one last thing and then we'll stop here. If you do the Laplace of y double prime, you get something similar. It's a little longer, but I'll jot it down here for you. You get s squared Laplace of y minus s times y of 0 minus y prime of 0. And you do this in the exact same way as we just did the last one, with one round of integration by parts and then sort of appeal to what we already discovered. So this would tell us that if we have an ODE, which we know is essentially made up of y's, y primes, and y double primes if it's second order, that all of those things could be transformed into s's, numbers, remember y and y prime of 0, those would be the two initial conditions, numbers. S, that's our new variable in transform land. And, okay, I'm going to have these Laplace of y characters. But aside from those being present, it looks like we're heading towards, again, a polynomial. What is this? I mean, if Laplace of y, maybe ignore that for a second, that's just a parabola. So it kind of seems like we're maybe going to have a way to attack an ODE doing maybe nothing but algebra. And some people, especially when we get to this part of the course, are like, oh my God, why didn't you tell us that we could do this all along? Well, okay. There will be some hard problems here in the next couple of weeks, but But for sure, actually, on simple ODEs that we've been solving all year, this technique, which we'll get to in the next video, might be better in some regards than doing it sort of the long way, or the old way, as we may call it. But there's definitely a time and place for doing Laplace transforms. So this isn't going to totally rock your world and be like, oh my gosh, I would have done this all semester, because these can get pretty nasty too. But okay, but for now, that's a good intro. So we certainly have a few questions remaining that we'll address in the next video, and pull this together into an actual strategy for how we're going to use this to solve ODEs and maybe get to our first solution or our first example of one. And then mostly what we'll do for the rest of our time is just sort of build up our capability to handle nastier or more interesting situations. So